Welcome to Lesson 9.1, Translate Figures and Use Vectors. So before we get into today's lesson, what you want to realize is that the majority of Chapter 9 relates to transformations and the properties of transformations. So to begin with, we're going to look at the definition of a transformation. So simply put, transformations are moves or changes a figure in some way. So a transformation simply moves or changes a figure in some way. It might be a turn, a slide, a reflection, and so on. So our goal for today is going to be using coordinate rules and vectors to translate a figure. And a translation you can think of as just a slide or a shift. So a translation is a type of transformation, and a translation is typically thought of just as sliding a figure. So when we're dealing with the transformation, we have a pre-image and an image. The pre-image is our original figure. The image is the new figure after the transformation. So if triangle ABC is our pre-image, then triangle A prime, B prime, C prime is the image. So the little apostrophe after the letter reads as the word prime. So triangle ABC becomes triangle A prime, B prime, C prime. So then anytime that you're dealing with a transformation, realize if we're seeing the apostrophe letters, that is our final image. If there's not the apostrophe letters, that's going to be our pre-image. So let's look at example 1. It says graph quadrilateral ABCD with vertices A, -1, 2, B, -1, 5, C, 4, 6, and D, 4, 2. So take a minute and graph those 4 points. You can see mine's already done here in blue. And then connect your 4 points with their segments to create this quadrilateral. Then what they want us to do is find the image of each vertex after the translation. And what this reads as is our original point, xy, our original coordinates, are being translated x plus 3, comma y minus 1. So what we'll do is we'll take the xy value, and for each point, we add 3 to the x, subtract 1 from the y, and that's our new coordinate. So if A was at -1, 2, A prime would be at x plus 3, y minus 1. So -1 plus 3, 2 minus 1, meaning A prime is at the coordinate 2, 1. Then we do the same process of adding 3 to the x value, subtracting 1 from the y value for points B, C, and D to get B prime at 2, 4, C prime at 7, 5, and D prime at 7, 1. So we're just using the transformation rule, or our translation rule right here. X value plus 3, y value minus 1. So this means we'll be moving right 3, down 1. So our new quadrilateral, A prime, B prime, C prime, D prime, is right here when we graph it. And prime notation is just that apostrophe. Example 2 gives us our translation right here. XY is being translated x plus 4, y minus 7. But what this is telling us, it says the image of xy, so our final image is the result of x plus 4, y minus 7. That is segment P prime Q prime. Those endpoints are P prime being at negative 3, 4, and Q prime being at 2, 1. Find the coordinates of the endpoints of the pre-image. So the key here is we're starting at the image, and we have to go back to the pre-image. So what that means is I need to take my original translation rule, x plus 4, y minus 7, and flip that to x minus 4, y plus 7, because we're going in reverse from the image back to the pre-image. So if P prime was at negative 3, 4, P would be at x minus 4, y plus 7, so negative 3 minus 4, 4 plus 7, giving us P's original coordinate for the pre-image at negative 7, 11. Then we do the same if Q prime was at 2, 1. We're working our translation backward. So x minus 4, y plus 7. So 2 minus 4, 1 plus 7 gives us Q's original coordinate of negative 2, 8. Then we get into a special type of transformation known as an isometry. And what an isometry is a transformation that preserves all lengths and all angle measures. In other words, we can call it a congruence transformation, because any isometry, the pre-image and the image are congruent. So a translation, a slide from, let's say, triangle ABC here to triangle A prime, B prime, C prime, a slide is a type of isometry, because when we're simply translating or sliding, we're not changing length and we're not changing angle measure. Then, just to keep in mind, for any translation rule that we're going to write, so example 3 asks us to write the rule. If we're going to the right, it's going to be our x value plus that number of spaces. If we're going left, it's x minus that number of spaces. If we go up, it's y plus the number. And if we go down, it's y minus the number. So let's look at example 3 to practice that. It says, write the rule for the translation of triangle ABC to triangle A prime, B prime, C prime. Then verify that the transformation is an isometry. So first off, we need to write the rule. Now, when I first looked at this, you can tell I originally thought it went down and right. Well, I was wrong though, because A prime, B prime, C prime is the one here on the left. That's our final image. The original pre-image is just ABC. So really what we're doing is we're moving each vertex up 1 and then left 4. So our translation would be up 1, left 4. So that means our x value minus 4, because we're moving left, and the y value plus 1. So to write our rule, it would be xy, translation arrow, and then it's x minus 4, y plus 1 in parentheses. And I'm not going to worry about the full verification, but what we can look at is we see when we move this triangle to this one, all the side lengths stay the same, all the angle measures stay the same. So that simply puts it to Theorem 9.1, the translation theorem, which states a translation is an isometry. So any translation, which you can think of as a slide or a shift, is an isometry, meaning the figures will remain congruent. So we looked at the notation, how we can write the rules for a translation, but there's another piece that we can use for this. We can use what's known as a vector. So a vector is a quantity that has both direction and magnitude. And magnitude we think of in math as size. So a vector is represented in a coordinate plane by an arrow drawn from one point to another. So you can think of it similar to a ray, but it doesn't go on forever. But it looks like one because it's an arrow. So we'll look at this box down here to look at our vector from F to G. Vector FG right there. So the diagram shows a vector named FG, reading vector FG. So the vector symbol is similar to a ray symbol, but it only has this one part of the arrow, this one barb. So this would read as vector XY. The initial point is that starting point of the vector, not the one by the arrow. It's our starting point. The terminal point is the ending point of the vector. So in this case, initial point would be F. Terminal point is G, the one by the arrow. Vectors always have two components. One is the horizontal component, meaning how far left or right it is going from the initial point to the terminal. So in this case, from F to G, it was 5 units right. The vertical component is how high up or down we move on the coordinate plane. So from F to G, it was 3 units up. So then what we use for vector notation is component form, combining the horizontal and vertical components. So the component form for vector FG is written as 5, 3 inside kind of these rigid brackets. So it's vector FG, and then instead of these rounded parentheses, it's more of these kind of greater than, less than brackets, which is our vector notation. And what this means is vector FG tells us that it would be a shift 5 units right, 3 units up. So name the vector and write it in component form. So in this case, we have BC. B is the initial point, C is the terminal. So we would write it as vector BC. Initial point first, terminal point second. From B to C, it was right 9, down 2. So our horizontal component always comes first. So right 9 is a positive 9, down 2 is a negative 2. In B, we have vector ST. Even though the vector is going left to, or right to left, we still write the vector symbol always going to the right. So vector ST is moving left 8, and the vertical component is just 0. There is no up or down. So if we're going left 8, we would just write that as negative 8, 0. In C, we have vector RS. So vector RS is moving right 5, up or down 0. So in component notation, it would be 5, 0. In D, we have vector TX, which is going up 3, no left or right movement. So in that case, it would be 0, 3. And then our last one is E here, which is vector BK, going left 5 and up 2. So left 5 would be a negative 5 in the X value, up 2 would be a positive 2 in the Y value. So we can use vectors in place of our translation rules here. So if we had a vector, negative 4, 1, that's the same thing as this translation rule, x minus 4, y plus 1. So we can go down and look at example 5, which tells us triangle ABC has vertices 0, 3, 2, 4, and 1, 0. So first, just graph that triangle. Over 0 up 3, over 2 up 4, over 1 up 0. Connect your points to get triangle ABC. Our vector, so it asks us to translate ABC using vector 5, -1. So the first value tells us right or left. +5 would be right 5. Second value, -1, means down 1. So what I do is I just take each coordinate, like for example here using B, and I would move it right 5, down 1. Then I'd take A, right 5, down 1. Take C, right 5, down 1. And now we have triangle A prime, B prime, C prime. So in B, vertices of triangle LMN are 2, 2, 5, 3, 9, 1. I know it goes off the coordinate plane, so just do your best to kind of estimate it. So right here is triangle LMN. Now our vector is -2, 6. So that means we're going left 2, up 6. So I'd take point L, go left 2, up 6. Take M, left 2, up 6. Take N, left 2, up 6. Label your points, L prime, M prime, N prime. Connect your points, and we have our image right here. So vector notation, which is our composite notation, or component notation, I should say. So component form for the vector, or our translation rules, both can be used to translate a figure.